Hello and welcome to Blueprint, our responsible manufacturing video podcast. I'm Björn, I'm heading the sustainability department at EOS, and I'm the proud host of this show. Today we're having our second episode, and it's all about the use and reuse of polymer or plastics materials. And as you can see, we're here in our showroom in Kreiling near Munich. Some machines are running, some colleagues are working, so I hope you don't mind. I'm honored to have two proven experts with me today, my dear colleagues, Sybille Fischer and Vanessa Seidenschwarz. Thank you for joining me today and welcome. And Vanessa, starting with you, can you shortly introduce yourself, please, and your role at EOS?
Thank you for having us, first of all. My role at EOS is a product manager for all polymer materials, and I'm developing our portfolio for polymer materials together with our R&D experts to fit to our customers' applications and needs.
Can you tell us a little bit more about what materials do we have?
So EOS portfolio is quite broad, so we have two types of materials, more the commodity materials and then the more specialized materials. In the commodity materials, there's mainly a polyamide materials where we have a PA11 or PA12, which you know from your everyday life, from your nylon stockings or your yogurt cups or maybe medical tubes or everything. And then the more specialized materials are the high performance materials, which are for usage in higher temperatures, or for example, also other materials like our TPU, which is a flexible material which you could use, for example, in shoe soles.
Thanks for that little introduction, Vanessa. Sybille, may I ask you to also introduce yourself shortly and your role at EOS?
Sure, and hello Björn, thanks for having us here today. I've been with EOS for more than 7 years. I'm a material developer, and initially I have taken care mainly of the development of our mid-temp materials, but in the last years I've changed more into a lot of pre-development and research projects. I'm taking care of some projects on my own, supporting others, and it's a lot of fun. And meanwhile, I'm also driving forward the topic of sustainability in material development together with my colleagues.
That's great to hear. And we've learned from Vanessa about the polymer materials that we have. Can you maybe let us know a bit more about the process, how we use them?
What we're having here at EOS is laser sintering, and laser sintering is a powder bed fusion process. This means that a polymer powder is applied layer-wise in the machine, and a laser melts selectively the areas where the later part is supposed to be solid. And then the next layer is applied, and so on. So in order for that to work, we have to preheat the powder until a temperature which is pretty close below the melting point, and the laser actually only applies the very last bit of energy for the polymer to actually melt.
And in this process that you just described, are there carbon emissions arising, or where do carbon emissions arising in this process?
So up to date, there are a couple of papers published from different people and institutions, and they showed that a great amount of the carbon emissions is coming from the material production itself, especially in the polyamides. And the rest of the carbon emissions is mainly driven by the process itself and the post-processing, and a big point of that is the electricity. So if we want to reduce these carbon emissions, we have 2 points. We can improve the material, or we can improve the process, or ideally both.
Mm-hmm. And I think there's also something like a refresh rate. Maybe you can explain that a bit more in detail, and why is it necessary to have a refresh rate?
As I mentioned earlier, we're having a hot process. This means the whole machine is at a temperature below the melting point. So if a polymer is kept at a certain temperature, it's damaged either by thermal stress due to the temperature or the time it's under temperature or other things. And in order to maintain material properties in the part itself, we have to add a certain amount of new powder. And typically that's a little bit more than it's actually used in the process.
Mm-hmm. And what types of damages do we see?
So as I just mentioned, we have the thermal stress we have in the polymer. That means the polymer is at a certain temperature for quite a long while, and this temperature degrades the polymer. In certain cases, such as the nylons, this could mean we have a molecular mass buildup, and this buildup leads to a higher viscosity of the melt, leading to process issues such as sink marks or a decreased interlayer bonding. On the other hand, we have the residual oxygen in the atmosphere of the machine, and this can lead to oxidations causing, for example, yellowing of parts or powder.
And is there anything that you can do about these kinds of damages within the process?
Sure, we can either improve the material or we can improve the process. On the material side, we could use, for example, stabilizers that prevent the buildup of the molecular mass or the oxidations. But on the other hand, this is not our core know-how, because we're not a polymer manufacturer. And we're doing our own research and we're looking into the process in order to understand them, but in the end, we're not the ones making the polymer. On the other hand, we do already offer some refreshed optimized powders such as PA2221.
So if I got you right, there's also a collaboration with the powder producers to limit the damage of the materials. Is that correct?
Yes.
Yeah. So Vanessa, can you tell us a little bit more about this collaboration with the powder suppliers? I mean, how can we imagine to look that?
Yeah, so basically, to understand the collaboration with our suppliers, we need to understand what is the core know-how of every party being involved. So we at EOS, we definitely know best what the powder technically has to look like to be processable in our laser sintering systems. So things like grain size or viscosity of the material, but we are not the chemical production experts. So that's where our partners and suppliers come into the collaboration. They bring the production know-how, the chemical production know-how to produce a material from a raw material and bring it into a form of a polymer powder. That's one thing. And then we have an additional step, bringing the polymer powder, the basic powder, which we get from our supplier, to another level, to post-process to become a laser sintering powder. And that's where our partner KVS, which is a sister company of EOS, comes into place with their know-how. And combining those three partners and their know-how, this is the way we develop our materials here at EOS.
So it's good to see that we collaborate along the supply chain here with our partners to improve that. Sybille, coming back to science, is there anything else we can do to prevent the damage within the process itself?
Sure. So I just said we have different things that actually damage our powder. And in the process, we can try to minimize all the things that degrade the polymer or that damage the polymer. And these are, on the one side, the temperature or the time the polymer sees the temperature. On the other side, the residual oxygen in the atmosphere. Talking about the temperature and the time. So if we, for example, have a faster process, higher build rates, our processes are much shorter. And in a way, that's a win-win situation, because we damage the powder less on the one side and our process is faster. This causes less emissions by having less heating, less electricity. On the other hand, we have the thing with the oxidation. So if we have a more pure atmosphere and a lesser oxygen content in the atmosphere, we can have less yellowing, yes, oxidative damage to the parts. And these are issues, both of them, the high build rates and the oxygen, that are addressed in recent developments and in new machine generations. These are points we are working on.
And I mean, the process parameters, I mean, they're core competency of EOS as well. So Vanessa, the question to you, have you ever thought about using those improved parameters to make it a product for the customers?
Yeah. Yes, we're definitely working on that currently, actually, already. As you said, we are on our home turf here, combining system, material, and developing a process for that. Always looking at things like keeping the mechanical properties, but also becoming a bit more sustainable, faster, all the aspects Sybille mentioned a minute ago. And we're actually currently developing a new parameter for our PA2200, like for all our commodity products, so customers can become more sustainable in their manufacturing processes with the existing materials they're already using.
So you say you're doing this for some, but is it also, I mean, or will it be in the future a prerequisite for any new material development that you're also looking at these kind of, let's say, sustainability improvements?
Definitely, it is already, we could say. As you know, our company purpose is responsible manufacturing, and we are always looking in options how we can act in that way as well. Either we can improve the material itself, or maybe we also can think about what might be a second life of the material if we can't reuse it in our processes maybe. So looking at the bigger picture of what we are producing, what our product.
So that's good to hear. I'm looking forward to that development, definitely. Sybille, we talked a lot about the process and the use phase in the machine, of the powder in the machine. But what about, I mean, what about waste? Is there generally waste created in the 3D printing process?
We just talked about refresh rates, and so far a common refresh rate would be 50%. This means 50% of the unused powder that's from the previous builds is mixed with 50% virgin powder. And of course, we don't use 50% of the powder in the process. So there's always some residual powder that cannot be reused. And in a way, yes, that's waste.
So there's some waste. Vanessa, is there anything we can do with that used powder?
Yes, we technically can do, because it's a bit difficult, the word waste in this case, because the powder which is waste, looking from our process, is not a real waste. It's a technically pure polymer powder, which is not usable anymore on our systems, but which can be used, for example, for injection molding or other additive processes like fused filament fabrication. And that's definitely where you could reuse that material to give it another life, let's say.
So there's options for that. Are we collaborating with any other company?
Yes, actually, we have been partnering since 2017 with a German partner, Kayu, and our partner takes the used powder from our customers, collects it, and then sells it to, for example, injection molding companies or other companies which can use that powder. And the nice aspect there is the revenue EOS gets from that is donated into social projects here around, locally around Kreiling.
Okay, so that's interesting to hear. It's not only that we found a second life for the used powder, but there's also a social benefit for that. I guess the reuse, or there's probably, in the reuse of the powder, there's probably also some challenges, or is it easy to do that?
In theory, it's always easy, I would say, but one aspect that's very important, we talked about waste, or the word waste, and that's the way we are currently using that material. It's just thrown into a waste bin. But if we want to reuse that material, we have to take care that it is not being mixed. For example, that you don't mix a TPU material with a polymer material. That's one point where we have to educate ourselves as well to work in that way. And then another aspect is, of course, the business case always behind it. Does it make sense to send 20 kilograms of a material across Europe to a partner that collects it somewhere else? Is this a good business case? There we see actually a few challenges currently with all the logistics. And then another aspect is like the regulatory restrictions we have. What is waste? How can we reuse it? yeah, that's a very tricky situation currently, but we are working on that.
So there's options available, but there's also some challenges, but I'm glad to hear that we're looking at those and trying to find solutions for them. Now, going away from the material more to the part, to the printed part, are there also options, Sybille, to do something with printed parts that are no longer used?
So we have quite a number of parts that don't even come to life because they're either prototypes and they just looked once, or they're test specimens. And we have a PhD thesis of my dear colleague Karl Freihardt, who is actually looking into that topic. He's trying to have a closed loop and recycle these parts into a laser sintering powder again. And his main focus is not on economics or viability. His focus is on a technical feasibility. So he's one of the first actually trying it, grinding it down, trying to restore the properties of the powder. And that's, I think, a really interesting topic, and I'm excited what the outcomes of this are.
So we're also in the beginning of this when I hear you. Is there anything else that we can do for the end of the life or of the normal life of that powder?
Yes, sure. So it always depends on how clean the parts are. The just mentioned test specimens are probably much easier to reuse than a part that has been in service for many years, maybe into harsh environmental conditions or heavily post-processed. But in the end, there are different ways I can recycle or reuse it. I can thermally recycle it. At least I get energy out of it in the end. I can use it as feedstock for other manufacturing techniques that have less demands for the material properties. Or, of course, I can look into biodegradability. I have on the one side biodegradable polymers itself, such as PLA, for example. They are biodegradable the way they are, and you could principally put it in landfill and they would degrade. EOS even has been part in a research project called Active Bone a couple of years ago, where they worked with PLA and they got it laser sinterable for implants, for example. On the other hand, our partners from EOS in North America have just filed a patent application where they actually add additives to polyamides like polyamide 11 or 12 that make them biodegradable. So they're polymers that are not biodegradable initially, and there are additives added that make them biodegradable. So they go back to soil when placed in landfill, and I think that's really exciting.
Mm-hmm. So that sounds like there's some ideas for new episodes, actually, once this is one step further in the process. So today we learned a lot about the use and the reuse of powder, and in our first episode we discovered that the material itself has a big impact on the carbon emissions, for example, of a process or of a 3D printed part. And we received some comments from the community. And one of the questions was if we also have bio-based materials. And maybe Vanessa, you can just say, give a short answer if we have something like that available as well.
Yes, actually we already have. Our PA1101 is a polyamide 11. And polyamide 11 is based on castor beans oil, so it's a renewable resource, and that we already have in our portfolio. Our sister company ALM is going already one step further. They even have a carbon neutral PA11 in their portfolio, which they added only last year.
Okay, that's interesting. We will have an episode on that one as well, I think. A very interesting project. Let me thank you for being my experts today. And we have a little present for you. So this is, on the one hand, our nice little hummingbird. One for you, Sybille.
I love it.
And one for you, Vanessa, representing our responsible manufacturing initiative. And we have a t-shirt as well with, let me show it, with the hummingbird.
Thank you very much.
That's for you.
Thanks for having us here.
Yeah, thank you very much. Thank you for listening in and watching this episode. And please stay tuned for our next show, which is coming up soon. Thank you, stay safe and take care.